Okay, welcome back. What we're going to talk about today is the chi-square goodness of fit. All right, and what we have here is when we're doing a chi-square goodness of fit test or chi-square test, there are some things that you have to know. It's a little bit different than what we talked about with one sample, two sample, um, p-test or t-test for p or m, all right, or the means, or the difference in means, and so on and so forth. So here we go. Well, first off, when you're doing chi-square goodness of fit test, we usually use it with categorical data. So that's the first thing you should know, all right? So we're going to talk about categorical, all right, data. Okay, so something that you maybe put in a pie chart or something like that. That's what we're going to be looking for. So goodness of fit test. So categorical data. The second thing that we want to look at is that when we're making our plan, is that we're going to or state, that is, we're going to state our hypothesis. Okay, and the expected values. So we have to know what our expected values are. So essentially our null hypothesis is this, that the claim of the distribution is true. So in context. So whatever the claim that they're making about a certain distribution or the categorical data, we're saying that's going to be true. Our null hypothesis is simply stating, all right, the claim of the distribution is not true, whatever that may be. Now, the thing is that we're going to have some observed values from a sample we have. And then we're going to need to know what our expected values are. Because if you recall, like a pie chart will have different percentages for the different distributions of the categories. And so what we want to do is want to take the expected values by taking whatever the proportion of each category is, multiplied by the sample size that we took, all right? And so from there, we want to know is that by figuring out, obviously with any test, if what they're saying is expected, all right, if it's true. And to do that, we're going to do a little proportion, and what's called the chi-square test statistic. And this little test statistic, all right, which looks like an x squared, but it's called a chi-squared, is going to be the sum of the observed values that we found in our sample minus the expected values of each category squared divided by the expected values. And we add those together, and what we have is what is known as the chi-square test statistic. All right, and then from here, we can find a p-value. All right, now how do we do that? Well, there's a certain distribution, all right, for chi-squared, because if you have observed minus expected, if the observed and the expected are the same, that means they're right on, we would have a value of 0, okay? So we would have all values of 0 if it's right on, if they're saying what say it is. So what we have is a chi-square distribution, okay, with a certain degrees of freedom. And we're going to have always start at 0. And what you know is that we should have, if it is true, most of the values will be close to 0, but then all of a sudden it's going to be leveling off, and we have some values, all right, depending on what we have, that will have, that will be skewed. So it's going to be skewed, all right, to the right, right? It's going to be skewed to the right. So that's what the distribution of a chi-squared is. And one cool note, all right, if we have this, is that our degrees of freedom is at the categories -1. And the p-values, we're going to use what is a table C, or you can use your calculator, and I'll show you that in a little bit. All right, and so our p-value is going to be what is the proportion, all right, for our chi-square statistic, whatever that is, all right, to actually count, all right, given the certain degrees of freedom. And one thing to note is that in a chi-square distribution, the mean is actually equal to the degrees of freedom. Okay, so wherever the mean is, okay, since this is skewed to the right, it's probably going to be somewhere slightly overpassed by the median. So if we go all right, we'll say that is df. Well, the larger the chi-square statistic is from the degrees of freedom, the greater the chances are that you're going to reject the null hypothesis. Okay, and that's what we know there. All right, so let's go through an example right here, okay, of doing this. And so what we have is, check our understanding. And you want to try this on your own, you can do this. And then we're going to have 3 questions we're going to do. All right, so Carrie made a 6-sided die in a ceramics class and rolled it 90 times to tell if each side was equally likely to show up. Okay, that seems all right. So she's trying to figure out, is it a fair die? Is it a fair die? So now from here, okay, the outcomes of each roll are this. 1 is 12, 2 is 28, 3 is 12, 4 is 13, 5 is 10, and 6 is 15. Okay, so on all of these, okay, these are our observed values. Now, before we get started, I'm just going to write out our expected values. Now, what is the expected values going to be? Okay, the expected values are going to be, well, as we said before, whatever the probability is all right, times our n value for each category. Well, since this is a die and there's 6 sides, we're assuming it's a fair die. And so our probability would be 1 over 6. Okay, 1 over 6. And if we take 1 over 6 times 90, all right, each one of these categories would equal 15. So we're expecting that we would get a 15 at each one of these values. Now, obviously, we know the law of large numbers is that if we were to do this, we have to do it many, many times. 90 is a lot of times, but not many, many, all right, and not an infinite amount of times. So this might be a little off. Now, the thing is that we're using the chi-square to see if it is statistically significantly off, okay? Because we see that 6 appears to be right on. This is a little bit, 4 is pretty close, but we have this suspicion that 2, all right, 2 is too weighted improperly, because obviously 28 is much larger than 15. And so now we're going to first state our hypothesis. So we're going to state the hypothesis of saying that the claim that the distribution all right of roles will be proportional. All right. All right. That's the claim that the distribution of roles will be proportional to the 6-sided die. Okay. So each role should be about 1/6. Now, the other claim is that the claim is false. All right. Or that the distribution is not proportional. The distribution, I know hypothesis would be that the claim that the distribution of roles proportional to, maybe I should put that 1/6 to the 6-sided die, will not be proportional to 1/6. Okay, so that's what we know right there. Okay, so for right here, we're just making our claim. All right, and now we want to calculate expected values. Well, we already did that for Ole, so we want to calculate the expected count for each of the possible values. Well, we did that up there, and so now the next thing we're going to do is we're going to look at and calculate the chi-squared statistic. So how do we do that? Well, essentially, if you recall, we're going to take the sum. Oops, that's a bad sigma. All right, we're going to take the sum. All right, of our observed minus our expected, all right, squared divided by our expected values, okay? And so what we're going to do is we're going to take, well, our first one, and I'm going to change this so you can see a little bit better. So we're going to take essentially our observed, which is 12 minus 15, we'll square that and divide it by 15. And then we're going to add that to the next one, which would be observed 28 minus expected. Oops, minus expected. All right, minus 15, which is our expected value for the second one. All right, squared divided by 15. And we would do this for every single roll, okay? For every single roll we have here. And we square it, divide by 15. And we can keep on going on. So on a test or quiz, usually on the AP test, you can just write the first one or two, and then go to the last one. Then we're going to write the last one right here. So then we're going to go 15 minus 15, which we know is going to be equal 0, divided by 15. And this will give us our chi-square statistic, okay? And so looking at this, we can realize that our chi-square statistic, and if you want to put this into our calculator, you can do this pretty well. And by doing that, first off, you want to do is go to your stat, and you want to go to edit. And in list 1, you want to put in all your observed values. And list 2, you want to put in your expected values. Okay, and you can do this actually on your calculator and figure all that stuff out as well. All right, but then from here, you want to go to stat, and you want to go to test. And if you go down here, all right, and I'm going to go up, and you go to, at least on this calculator, if you go to chi-square GOF, greatest goodness of fit test, we're going to press enter there. And it's going to ask you, okay, observed is going to be our list 1, expected list 2. we have 5, or actually 6 categories. So we're going to have 6 minus 1 is our degrees of freedom. So we have that. And then we're going to go down here and we're going to calculate that. All right, we're going to calculate that. And this is what we have here. So it says our chi-square statistic is going to be 14.4. It says our p-value is going to be 0.013. All right, and we have degrees of freedom of 5. Okay, and then we can see our contributing factors, because now right here, these are each one of the individual statistics that we have up there. So if you go, all right, and write that down. Oops, I did the wrong thing, sorry. All right, and if you go back and do that, you can see each one of these values right there. Okay, and I believe it's 14.4, and so that is where we can see, all right, what the values are. Okay, oops, there we go. Which degrees of freedom do we use? All right, degrees of freedom, as we said before, is going to be 6 minus 1, which is 5. All right, and then we went on there, and what conclusion can we make? Well, if we have, I believe it's 0.014, all right, 0.014, that is our p-value. Okay, and you can use a table C. I used a calculator in doing that. And so if I want to do that again, once again, over here, go to test. All right, go down. All right, and we're going to press D. I should have just brought that up. I apologize. All right, boom, 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 and boom. All right, and we have 0.013. Oops, 0.1013. And so what conclusion can we make? Well, since we have right here is depending on what our alpha level is, if we said 0.05, well, this is definitely going to be less than 0.05. So at least we could say that we would reject, all right, reject the null, all right, because 0.013 is less than 0.05. Okay, we have convincing evidence, all right, that the die is not fair. Okay, and if we want to make an even stronger conclusion, we can say that it appears to probably be weighted, because this appears to be weighted to 2. All right, it appears to be weighted to 2. All right, so 2. And why is that? Because we see the greater difference. So that had the biggest contribution to creating this, all right, chi-square level, all right, which made it not or significantly different or non-proportional from the null. All right. Well, I hope that helps you out. All right. And yeah, good luck and God bless in the rest of the problems.